we've already seen that for motion graphs, we can learn a lot about what the object is doing by looking at the slope of the line on that graph. We're now also going to look at what we can learn by analyzing the area underneath the line on the graph, or the area underneath the curve, if we want to call it that. Now, we sometimes call it the curve on the graph, but here in grade 11 physics, we're only going to deal with straight lines. If we did want to calculate the area that was under a curve, we'd need to use calculus in that case. But for us, we're going to stick with straight lines to try and keep this introductory note a little bit simpler. So for example, if we had an AT graph, so this is acceleration versus time, and those dots along the top are representing the different points in time of that object undergoing a specific acceleration. So in this case, you can see that it's clearly going at 10 meters per second squared the entire time as it goes along. So if we want to talk about the area underneath that, well, we need some points to mark off. So we have some starting point in time at the origin, and then let's choose some later point in time. And once we've chosen some later point in time, there's some amount of time that's gone by in between. And if we draw just a little quick dotted line down from the original line that we had, we see that this is now forming a rectangle shape. So this rectangle is what we're trying to find the area of. And we're trying to figure out what actual meaning it has when we find it. So if we did try and calculate the area, we have to ask ourselves, what are we actually calculating? Well, of course, area of a rectangle is length times width. But those have some specific names on our axes. So the length and the width are actually acceleration and time. And so length times width in our case is a multiplied by t, or at. So if we just stop and think for a second about what units that would have, well, acceleration has a unit of meters per second squared. We then multiply that by a unit of seconds for time. And when we do that, what actually happens is that one of our seconds actually cancels out the second power of seconds at the bottom of the meters per second squared. So what we end up having is an overall unit of meters per second. So we didn't really know exactly what we were trying to calculate there, but when we did find that area, find acceleration multiplied by time, we ended up getting something with units of meters per second. Well, what does that actually mean? Well, we know what's measured in meters per second. It's velocity. So the area below an AT curve is actually telling you a velocity. Specifically, it's telling us what velocity that object has reached once it gets to that final point in time that we marked off on the graph. So overall, if we wanted to find the velocity of an object after, for example, 3 seconds, we would just find the area under the curve from the 0 marker on the time axis all the way to the 3-second marker on the time axis. And once we found that entire area, we found the velocity at that point in time. So that's what we got when we used an AT graph. But what about if we had a VT graph, velocity versus time graph, that looked very similar, really identical, other than its axes? So here we see a VT graph, and now we have an object that's traveling at a constant velocity of 10 meters per second. And we want to know, what does this meaning actually tell us? Well, again, we think about specific points in time, some initial time 0, and then some later time that we're interested in. And to make it a rectangle, we can just draw a little dotted line that comes down from our original line. And so once again, it's this whole section in here that we're referring to when we talk about figuring out what the area under that curve is. So now if we look more specifically at what we're doing with a VT graph, well, we're doing length times width to still find the area, but now it's V multiplied by T. So if we think again in terms of units, we've got velocity, which is being measured in meters per second, and we're multiplying it by seconds once again. That's our time unit. And when that happens, we get the seconds that we multiplied from time canceling out the seconds that we're dividing the meters per second unit. So we're actually just left with the meters part. And so we got a value that is measured in meters. And so the area below a VT graph is actually a displacement. Displacement being measured in meters. So if we travel for 5 seconds at 10 meters per second, we just need to find the area underneath that graph. And that'll tell us the total displacement or the total amount of distance in a particular direction that has been covered. And now is a good time to summarize some of the patterns that you might be noticing at this stage. The pattern that we are starting to see with area is actually the opposite pattern that you might have noticed with slope. So this little summary chart might help to summarize that a little bit. If we've got displacement originally, you can go from displacement and find the slope of that to find its velocity. Then if you have velocity, and you have an entire graph of velocity versus time, you can find the slope of that line at any particular point in time, and it'll tell you the acceleration of the object at that point in time. What we just did was work backwards. We then started with an acceleration time graph, and we realized that when we found the area of it, the area under that acceleration time graph gave us velocity. Then when we looked at a velocity time graph, the area underneath that gave us displacement. And so all three graphs, you can see, are strongly connected to one another. And there's an opposite relation between finding the slope of the line and finding the area underneath the curve. But both methods can be used to find one of the kinds of motion graphs that you don't know initially. So let's see an example that we can solve now using this method. And we're not going to use any new fancy equations to do it. We're just going to use what we know about area, and specifically finding the areas of rectangles like we've been doing so far. So we've got a jet plane that's accelerating at a rate of 3.00 meters per second squared during its takeoff. We're going to try and determine the plane's velocity at 4 different points in time, at t equals 1 second, at t equals 2 seconds, t equals 3 seconds, and 4 seconds. For starters, though, it might be useful just to quickly sketch out a diagram of this motion graph. So if we're given information about the acceleration of this jet plane, then we actually have enough information to draw an AT graph. And specifically, this is just a very rough sketch. It doesn't need to be anything fancy. At 3.00 meters per second, we've got a plane that is flying at a nice, straight, constant acceleration rate. Not necessarily constant velocity. We know that it's increasing its velocity, but it's a constant acceleration rate. And then we've got some various points in time. So we'll mark off a point at t1, at t2, at t3, and t4. Again, doesn't have to be perfect, just needs to be able to give us a rough idea of what's going on. And then coming down to each point in time, we are going to try and find the area of each of those. So let's break this up to organize it a little bit. First off, that's just my symbol to say at t equals 1. So at time equals 1, we're going to do some solving and figure out what we need. Then we're going to do at time equals 2, do a little bit of solving and figure that out. At time equals 3, and we'll do some solving and figure that out. And then once I've done those 3, I'm going to leave the last one 4 seconds for you to try and finish off yourselves. So in our case, if I'm trying to find the velocity at t equals 1, or in other words, after time has gone through 1 full second, remember, all I'm doing at this stage is area. And area equals L times W, length times width. And for these particular problems, when you're just finding areas, I'm okay if we get a little bit loose with our significant digits and including our units. So I'm just going to be a little more rough about it and say that our length and our width are, in this case, 3 meters per second squared multiplied by 1 second of time. When we do get a final answer, though, in this case 3, we know that it has a unit of meters per second because we've already analyzed these graphs to realize that the area underneath an acceleration graph gives me the velocity, 3 meters per second. And so that, what I just found, is just this first area. The area under this first chunk. At t equals 2, it's the same idea. Area is still equal to length times width, but in this case, after 2 seconds have gone by, the length could still be 3 meters per second squared from the acceleration, but now I'm just multiplying by 2 seconds that have gone by. And again, when I get my answer of 6, I know that it's actually equal to 6 meters per second. At that stage now, I've found all of the area up to this point. Using my fabulous coloring skills, of course. And you're hopefully kind of getting the hang of it by now. Still area equals length times width, which by this third second is 3 meters per second squared multiplied by 3 seconds that have gone by. And so we get 9, and specifically we know that it's 9 meters per second. So after 1 second, it's going 3 meters per second. After 2, it's 6. After 3, it's 9. You can probably guess off the top of your head what t equals 4 will be, but I want you to take another minute in your own notes and finish it off by showing how you would calculate for t equals 4. But of course, by this stage, where I've gotten to, I have only found the area under the curve up to this point, up through the first 3 seconds. But there is still one chunk in here that I leave for you to try and solve and finish off. And that will give you an overall sense of what that velocity would be at 4 seconds. The final example at the bottom is just a velocity time graph, and you're trying to use it to find displacement. So once again, that means if we're finding displacement from a velocity time graph, that means that you'll just need to find the area underneath that entire line. And so that might mean using some things from previous grades like composite figures. But we'll talk a little bit about that in class if you're struggling with it. And make sure you're trying the practice questions associated with this note.